Technology. 17. Machine learning.
Teaching computers to learn.
1. Definition of machine learning. Machine learning is a branch of artificial intelligence that focuses on developing algorithms and models that enable computers to learn from data and make predictions or decisions without being explicitly programmed. It involves the development of computational models that can analyze and interpret data, recognize patterns, and make informed decisions or predictions based on the patterns identified. The primary goal of machine learning is to enable computers to learn and improve from experience, similar to how humans learn from observation and practice. Machine learning algorithms and models are designed to automatically adapt and adjust their behavior based on the input data, allowing them to perform tasks more accurately and efficiently over time. 2. Data-driven approach. Machine learning relies on data as the primary source of information for training and improving algorithms. The data-driven approach involves feeding large amounts of data into machine learning models, enabling them to automatically learn patterns, relationships, and dependencies within the data. The quality and quantity of the data used for training directly impact the performance and accuracy of the machine learning models. By analyzing and processing vast amounts of data, machine learning algorithms can uncover insights, discover hidden patterns, and make predictions or decisions based on the patterns observed. The data-driven approach empowers machines to leverage the information contained in the data to learn and improve their performance, enabling them to tackle complex tasks that may be challenging or time-consuming for humans. 3. Pattern recognition. Machine learning algorithms are designed to recognize patterns and relationships in data to make accurate predictions or classifications. These algorithms can identify and extract meaningful features or representations from the input data, enabling them to generalize from known patterns and apply this knowledge to unseen data. Pattern recognition is a fundamental aspect of machine learning, as it allows models to learn from historical data and make informed predictions or decisions based on the patterns they have identified. By detecting and understanding patterns, machine learning algorithms can perform tasks such as image recognition, speech recognition, anomaly detection, and sentiment analysis. Pattern recognition enables machines to discern complex structures and relationships within data, enabling them to automate tasks and provide valuable insights. 4. Supervised learning. In supervised learning, algorithms are trained using labeled data, where the desired output or target variable is provided for each input data point. The labeled data serves as a training set, allowing the machine learning algorithm to learn the mapping between the input data and the corresponding output. During the training phase, the algorithm adjusts its internal parameters to minimize the difference between its predicted output and the true labels. Once trained, the algorithm can make predictions or classifications for new, unseen data. Supervised learning is widely used in various applications, such as regression tasks to predict numerical values or classification tasks to assign data points to predefined categories. It is an effective approach when labeled data is available and serves as a basis for training accurate and reliable machine learning models. 5. Unsupervised learning. Unsupervised learning algorithms discover patterns in unlabeled data, identifying hidden structures and relationships. Unlike supervised learning, unsupervised learning does not require labeled data or explicit feedback. Instead, the algorithms analyze the inherent structure and patterns within the data to uncover meaningful representations or groupings. Unsupervised learning can be used for tasks such as clustering, where similar data points are grouped together based on their inherent similarities, or dimensionality reduction, where the algorithms identify and extract the most relevant features from the data. Unsupervised learning is particularly useful in scenarios where labeled data is scarce or unavailable, as it allows for exploratory data analysis and the discovery of novel insights and patterns. 6. Feature extraction. Machine learning involves extracting relevant features or characteristics from raw data to represent and capture important information. Feature extraction plays a crucial role in machine learning as it involves transforming the input data into a format that is suitable for analysis and modeling. The process of feature extraction entails identifying and selecting the most informative attributes or properties that contribute to the task at hand. This step helps reduce the dimensionality of the data, remove noise or irrelevant information, and highlight the essential characteristics that are relevant for making accurate predictions or decisions. Feature extraction techniques can range from simple statistical measurements to complex algorithms that automatically learn the representations directly from the data. Effective feature extraction is critical for building robust and efficient machine learning models that can generalize well to unseen data. 7. Regression analysis. Machine learning includes regression analysis, which models the relationships between variables to predict numerical values. Regression analysis aims to understand the dependencies between the input variables, often referred to as features or independent variables, and the target variable, also known as the dependent variable. The goal is to develop a regression model that can estimate or predict the numerical value of the target variable based on the input features. Regression models can capture linear or nonlinear relationships and are widely used for tasks such as sales forecasting, stock market prediction, and housing price estimation. Machine learning algorithms optimize the regression models using training data to learn the underlying patterns and relationships, enabling accurate predictions for new, unseen data. 8. Classification tasks. Machine learning algorithms can classify data into predefined categories or classes based on their learned patterns. Classification is a fundamental task in machine learning and is used in various applications, such as spam email detection, sentiment analysis, image classification, and disease diagnosis. Classification algorithms learn from labeled training data, where each data point is associated with a specific class or category. The algorithms analyze the features of the data and develop decision boundaries or decision rules to assign new, unseen data points to the appropriate classes. Classification models can be binary, where there are only two possible classes, or multi-class, where there are multiple classes to choose from. Through the classification process, machine learning algorithms enable automated decision-making and accurate categorization of diverse types of data. 9. Clustering algorithms. Machine learning includes clustering algorithms that group similar data points together based on their inherent similarities. Clustering is an unsupervised learning technique that aims to discover patterns in structures and data without prior knowledge of the classes or categories. Clustering algorithms analyze the features of the data and group data points that exhibit similar characteristics, forming clusters or subgroups. The goal is to maximize the similarity within each cluster while maximizing the dissimilarity between different clusters. Clustering algorithms are used in various domains, including customer segmentation, image segmentation, and anomaly detection. They provide insights into the natural groupings and associations present in the data, allowing for exploratory data analysis and pattern discovery. 10. Dimensionality reduction. Machine learning techniques can reduce the dimensionality of complex data by extracting the most informative features. Dimensionality reduction is crucial when dealing with high-dimensional data, where the number of features or variables is large. High dimensionality can pose challenges in terms of computational complexity, overfitting, and noise amplification. Dimensionality reduction algorithms aim to transform the data into a lower dimensional representation while preserving as much information as possible. These algorithms identify the most relevant features or create new combinations of features that capture the essential characteristics of the data. By reducing dimensionality, machine learning models become more interpretable, computationally efficient, and robust against noise and redundant information. 11. Neural networks. Machine learning utilizes artificial neural networks, which are inspired by the structure and function of biological brains, to model complex relationships. Neural networks consist of interconnected nodes, or artificial neurons, organized into layers. Each neuron processes and transmits information to other neurons, mimicking the way neurons in the human brain communicate. Neural networks excel at capturing nonlinear relationships and handling complex data, making them suitable for tasks such as image recognition, natural language processing, and speech synthesis. The networks learn from data by adjusting the strengths of connections, known as weights, based on the patterns and relationships they identify. During the training process, the neural network iteratively adjusts these weights to minimize the difference between its predicted output and the true output. This optimization process, often performed using gradient-based algorithms, allows the neural network to learn and generalize from the training data, enabling it to make accurate predictions or classifications for new, unseen data. Neural networks can have multiple hidden layers, referred to as deep neural networks, which allow for the modeling of highly complex relationships and the extraction of hierarchical representations from the data. Through their ability to learn and adapt from data, neural networks form the foundation for many advanced machine learning techniques, such as deep learning. 12. Deep learning. Deep learning is a subset of machine learning that focuses on training deep neural networks with multiple hidden layers. Deep learning models leverage the power of deep neural networks to automatically learn and extract hierarchical representations of the data. These models excel at learning from large amounts of data and can capture intricate patterns and relationships. Deep learning has revolutionized various fields, including computer vision, natural language processing, and speech recognition. It has achieved remarkable performance in tasks such as image classification, object detection, machine translation, and voice synthesis. Deep learning models learn directly from raw data, bypassing the need for manual feature engineering, and can automatically discover complex features and representations that lead to superior performance. The depth and complexity of deep learning models enable them to handle highly challenging and diverse tasks, contributing to significant advancements in artificial intelligence.
13.
Natural language processing. Machine learning techniques are applied to natural language processing tasks, such as speech recognition, sentiment analysis, and language translation.
Natural language processing, NLP, focuses on enabling computers to understand, interpret, and generate human language. Machine learning algorithms play a crucial role in NLP by providing methods to process and analyze text data.
NLP models can be trained to recognize speech patterns, extract meaning from text, classify sentiment or emotions, generate human-like text, and facilitate language translation. By leveraging machine learning techniques, NLP applications have become more accurate and sophisticated, enabling advancements in voice assistants, chatbots, language understanding, and text analytics. NLP models learn from large text corpora and can capture the semantic and syntactic structures of language, allowing for automated language processing and understanding.
14. Reinforcement learning. Reinforcement learning is a type of machine learning where an agent learns through interaction with an environment, receiving rewards or penalties based on its actions.
Reinforcement learning is inspired by how humans and animals learn to navigate and make decisions in dynamic and uncertain environments. The agent, typically represented by a machine learning model, takes actions in the environment and receives feedback in the form of rewards or punishments. The goal of the agent is to learn an optimal policy, a sequence of actions, that maximizes its cumulative reward over time. Reinforcement learning has applications in various domains, including robotics, game playing, autonomous vehicles, and recommendation systems. It enables machines to learn and adapt to changing conditions, explore different strategies, and optimize their decision-making processes based on trial and error.
15. Model evaluation. Machine learning models are evaluated using various metrics to assess their performance and generalization ability. Model evaluation is a critical step in the machine learning pipeline to ensure that the trained model can effectively make predictions or decisions on new, unseen data. Evaluation metrics depend on the specific task and the type of data being analyzed. For regression tasks, common evaluation metrics include mean squared error, mean absolute error, and R-squared. For classification tasks, metrics such as accuracy, precision, recall, and F1 score are often used. Model evaluation involves splitting the data into training and testing sets, where the testing set represents unseen data. The model's predictions on the testing set are compared to the true labels or values to calculate the evaluation metrics. Proper model evaluation helps assess the model's performance, detect potential issues such as overfitting or underfitting, and guide further model refinement and optimization. 16. Feature engineering. Feature engineering is the process of selecting, transforming, or creating features to improve the performance of machine learning models. Feature engineering is a crucial step in the machine learning pipeline as it directly impacts the model's ability to extract meaningful patterns from the data. It involves identifying the most informative features, removing irrelevant or noisy features, and creating new features that enhance the model's predictive power. Feature engineering requires domain knowledge and understanding of the problem at hand. Techniques such as normalization, scaling, one-hot encoding, and feature selection help pre-process and enhance the features. Well-engineered features can lead to more accurate and robust machine learning models, as they capture the essential characteristics and reduce the complexity of the learning task. 17. Model training. Machine learning models are trained by optimizing their parameters using algorithms like gradient descent or stochastic gradient descent. Model training involves adjusting the internal parameters of the model to minimize the difference between its predicted outputs and the true labels or values in the training data. The optimization process aims to find the best set of parameters that optimize a specific objective or loss function. During training, the model iteratively updates its parameters based on the gradient of the loss function, gradually improving its performance. The training process involves feeding the training data into the model, computing the predicted outputs, comparing them with the true labels, and updating the parameters accordingly. The model continues this iterative process until convergence, where further updates do not significantly improve its performance. Proper model training is essential to ensure the model learns meaningful patterns from the data and can generalize well to unseen data. 18. Overfitting and underfitting. Machine learning models can suffer from overfitting, where they become too complex and perform well on training data but poorly on unseen data, or underfitting, where they fail to capture the underlying patterns in the data. Overfitting occurs when the model learns the noise or random fluctuations in the training data, leading to poor generalization to new data. Underfitting, on the other hand, occurs when the model is too simplistic or lacks the capacity to capture the complexities of the data. Balancing between overfitting and underfitting is crucial to achieve good model performance.
Techniques such as regularization, cross-validation, and early stopping help mitigate overfitting and underfitting issues. Regularization methods introduce penalties to the model's complexity, cross-validation helps assess the model's performance on unseen data, and early stopping stops the training process when the model's performance on validation data deteriorates. Finding the right balance between model complexity and generalization ability is a key challenge in machine learning.
19. Transfer learning. Transfer learning is a technique in machine learning where knowledge gained from one task or domain is applied to another related task or domain.
Transfer learning leverages the idea that models trained on large and diverse datasets can capture general features and representations that are applicable to other tasks or domains. Rather than training a model from scratch for a specific task, transfer learning enables the reuse of pre-trained models and their learned representations as a starting point. This approach is particularly useful in scenarios where the target task has limited labeled data or the computational resources for training from scratch are constrained. By transferring knowledge from a source task to a target task, transfer learning can significantly improve the performance and convergence speed of machine learning models. It allows models to benefit from previous learning experiences and generalizes well to new tasks or domains.
20. Model deployment. Trained machine learning models are deployed to production environments to make predictions or provide decision support in real-time applications. Model deployment involves integrating the trained model into an operational system or software infrastructure, where IT can receive input data, process it, and generate predictions or decisions. Model deployment requires considerations such as scalability, reliability, and latency, as the deployed model should be able to handle real-time data streams and respond quickly. Deployment also involves managing the model's lifecycle, including versioning, monitoring, and updating to ensure optimal performance over time. Depending on the application, the deployed model can be embedded in an application, accessed through an API, or integrated into a larger system. Proper model deployment is essential to realize the benefits of machine learning in practical settings, enabling automated decision-making, personalized recommendations, fraud detection, and other real-time applications. 21. Continual learning. Machine learning algorithms and models can be updated and refined over time as new data becomes available, allowing for continual learning and improvement. Continual learning, also known as lifelong learning or incremental learning, refers to the ability of machine learning systems to adapt and incorporate new information without forgetting previously learned knowledge. Rather than retraining the models from scratch, continual learning involves updating the models incrementally to incorporate new data or adapt to changing conditions. This process allows the models to evolve and refine their predictions or decisions as they encounter new situations. Continual learning is particularly relevant in dynamic environments where data distributions or task requirements may change over time. It enables machine learning systems to adapt, remain up to date, and maintain their performance and accuracy in evolving scenarios. Continual learning techniques are being actively researched and developed to overcome challenges such as catastrophic forgetting and the efficient use of computational resources, enabling lifelong learning capabilities for machine learning models. Thanks for watching. Please like, share and subscribe, and comment below if you agree, or would like to add your thoughts.